Um, so before I get into today's lesson, I wanted to ask, based on the practice one we did with that sheet last time, and I sent out, hopefully, to everyone that you got the kind of my version of the answers of anything. And so I was curious from that if you guys had any lingering comments or questions or frustrations or additional things that you guys were looking for on that practice. And I got some feedback of people saying it was useful, some people saying it was useful, but also they were confused on a few things. So I was just curious if there was any general, even if it's something that you have since figured out, where the rough spots on that, so I can kind of know where we should be emphasizing as we move forward. Okay, I'm going to assume that that's long and deathly silence was not because my mission net cut out, but because you guys are all feeling good about that. So we're going to do something a little bit similar today, because today is not doesn't have a whole. I know I've been banging this drum a lot, but it's true. We don't have a lot of new stuff today. We're going to talk, kind of cut to the chase. Today's lesson is about doing confidence intervals and hypothesis tests for the linear regression we've been doing. But before we get there, I want to do a deep dive into understanding the linear regression model that R spits out. I say deep dive, not incredibly deep, but more than we did before. Okay, so so I should click on the correct screen and then go forward. So before we get into that, just a quick reminder, I'm going to try to foot stomp this each time, that this is y equals beta naught plus beta 1x plus e. That is the equation, right? That is what's happening in real life. It's the thing we'll never actually know, right? It's the actual response variable and how it equals the axial linear relationship, which is the average y for a given x, and then we're adding on this normal error, right? Basically, in a kind of summary version, this top part, this is reality that uses parameters, because that's what beta naught and beta 1 are. They are parameters that we will never know, and a random variable epsilon that we can never predict, right? So this is going back to when we were doing tests and we wanted to figure out the proportion p. That was a parameter that we didn't know. Or when we wanted to figure out the overall mean mu, right? Mu was a parameter that we would never know. Same thing here, right? Beta naught and beta 1 are the parameters for the actual model that we will never know. And even if we did, it wouldn't be perfect, because there'd still be this E error representing random variables, right? In comparison, what we are trying to figure out is we are going to make a linear estimate. That's what y equals beta naught hat plus beta 1 hat x, right? This is a linear estimate that uses the statistics beta naught hat and beta 1 hat that are derived from the sample. So these are what we made from the sample that are our best estimates of the actual parameters that we'll never know. And it ignores error. When we look at the residuals, that's representative of our error, but we're not going to try to capture that in our equation. We are just making an equation for a line that estimates, uses estimates of the parameters, or the actual parameters that we will never know. So before we go any farther, any questions on the difference between these two things? Because I want to make sure, A, you guys understand them conceptually, but B, also for when you guys do the explanations, because there still seems to be some either misunderstanding or, at best case scenario, just laziness of being clear with your words. And I've had to ding people on labs because they'll say something like, on our null hypothesis is bar equals 32. No, it's not, because x bar is not a parameter. Our null hypothesis is that mu equals 32, because our hypothesis, what we're guessing is that the parameter equals 32. We will never have a hypothesis about sample statistics, because we made those. We know what they are. There's no need to hypothesis. I'm 100% sure what X bar is. I'm 100% sure what beta naught hat is. What I'm not sure is what beta naught is. What I'm not sure is what mu is. And so it's important you understand the difference between parameters and our sample statistics. Man, I love coffee so much, it's ridiculous. Okay, and math. Okay, so here is based on what we, our example that we did last time, this is the linear model summary from the regression we were doing, right? And so this is, it's, excuse me, this is the model has a much more to do with it, but this is what we get when we spit out the summary, right? And it is basically one-stop shopping for anything we would need to know about the model. And so, like I said before, R is going to do all the heavy lifting, but that makes it doubly important that you understand what things mean and how to grab them out of it. So that's what we're going to do here before we get into doing any of the testing. So first of all, some of these things we already talked about, and I'll go over fast. So this first top two parts, that call at the top, that is just saying, hey, reminder, this is the relationship that you're analyzing, right? And so this is saying what you asked for was a linear model, and I'm going to give you the formula and information about revenue versus budget, right? And so that line is actually not inconsequential because the order matters. That is reminding you to say, hey, this is what I'm giving you information about. If this isn't what you wanted, you need to redo it, right? Whether maybe it's the wrong variables there, or here it's or maybe it's the wrong order, right? Because this is saying, I am going to do a linear model of seeing how revenue responds to budget, right? If you had budget tilde revenue, then that would be saying a different thing. That would be saying, I'm going to do a model of how budget responds to revenue, which if you saw that in the first line, you'd say, oh, that doesn't make sense. That's not what I wanted. So make sure that first line there is what you intended, and it is in the order that you intended. That second section there, those are the residual quartiles. It's just information about the residuals, meaning the distances of the observations or the dots from the line we came up with. We don't usually use this information, but it can be handy as kind of a general idea. It's basically showing you all the quartiles. Min is basically the 0th quartile. So the min, the first, the median, the third quartile, and the max of the residual. So at a glance, I can see, hey, the biggest quartile is what? That's 1,000, that's hundreds, thousands, millions. So I have some big quartiles, but I'm talking about movie revenue and budgets, which go into the hundreds of millions of dollars, right? So that's not as big a deal. Depending on what I was looking at, maybe that would be a bigger deal. Okay, here are probably the two of the most important things on the sheet. We talked about this before, but I'm going to foot stomp them again. These are your coefficients. These are the estimates. This is beta naught hat and beta 1 hat, right? And so it's called coefficients, right? Because ultimately what we're making is this line, right? Y equals beta naught hat plus beta 1 hat X, right? And so this right here is the estimate for the coefficient for budget, and our budget variable is X. So it's saying, this is my estimate for the coefficient of the budget variable, of the X variable. And so it is saying the real coefficient is beta 1. Here is my estimate of it, which is beta 1 hat. Same thing for the intercept. The intercept is saying, this is my coefficient for, well, there's no variable, it's the intercept. And so it is the estimate of beta naught, which is beta naught hat. And so those are your two estimates of your coefficients there. That is what is going to define our estimate line for the least regression line. Before we go any farther, any questions on what we've looked at so far as numbers? Okay. Next one is this R squared value. And I think there was at least one class that I said the wrong thing, and I think it may have been you guys. I think I told you guys to use this adjusted, and I was wrong on that. Well, when we want to use r squared, we want to use this r squared on the left, this one that says multiple r squared. We'll talk about this one later, and you'll notice they're almost the same right here. That one on the right, without getting into it, that is like it says, an adjusted value, that when we start using more variables, meaning that right now we're saying, hey, how is revenue a result of budget? Later on, we can talk a little bit about, well, maybe it's more than just budget. Maybe it's a combination of budget and what month it comes out and how many star actors are in it, and also how many prequels there were, right? And so I have 4 variables, and I have one big long equation that relates to all 4 of those variables. And so when I do that, this takes the r squared value and adjusts it based on the number of variables to make a fair comparison. But we don't need to worry about that. We just need to worry about this one right here. This is the r squared, right? And so we talked originally about r. And so if I do, that is r squared right there. So if I take the square root of it, which would be, I don't know, a little bit over 0.7, that would be my r, right? And we said the r was a correlation coefficient that said, hey, if it's 1, then it's a perfect, all the dots are on the line and it's going up. If it's -1, then it's a perfect, but with a negative slope. And anywhere in between is a measure. So this one, for the r being around 0.7, is pretty good. That means I've got a strong positive linear correlation. However, we usually use r squared instead of r because it has more real world meaning. The r squared is a measure of how much the model reduces or explains variance, right? So in this case, I've got an r squared of 0.4078, which means that 40.78% of the variance is explained. We talked about it last time, right? That means that I might have a model where the data looks like this, right? And if I just look at the variance in the y, I go, wow, it varies all the way from here to here, and I can maybe make a box plot. And so that's a lot of variance. But when I do my linear model, I go, wow, those are all close. If I look at the variance of the residuals, so if I look at a graph of the residuals, I go, actually, the residuals are only very small, positive, negative. And now when I look at the variance, it is very small, right? And so the y has a lot of variance, but that's because I wasn't thinking of it as a linear relationship. When I look at it in comparison to a line we've made, the variance is much better. And so that r squared is a measure of what percentage the variance is reduced, meaning what percentage of the variance is explained by our line or by our model, right? So that is why we like to use r squared, because it has that additional meaning. Any questions on r squared, what it means, and how it's useful? So the highest r squared could be is 1, because a 1 would mean that all the dots are on the line, which means that it had some variance, but when I look at it in comparison to the line, there's no variance because they're all on the line. And so an r squared of 1 would mean that I reduced 100% of the variation. Never happens, but that's what that would mean. Okay. Now, the part we didn't really talk about as much is the numbers remaining on the right here. And all these numbers on the right have to do with a hypothesis test, right? And so the hypothesis test is the null hypothesis is going to be that one of our parameters, that's why I put beta sub I, because this could be for beta naught or beta 1, either way, is 0. And that the alternative is that it is not 0. Normally, we don't care about beta naught. Sometimes we do, but normally we care about beta 1, because if my null hypothesis is that beta 1 equals 0, remember, my overall equation that I'm trying to model is y equals beta naught plus beta 1x plus epsilon, right? If my null hypothesis is that beta 1 equals 0, then what I'm saying, that is the equivalent to saying there is no linear relationship, right? Because if beta 1 here is 0, then that means the coefficient of the x variable is 0, which means y does not correlate, does not change on x. Changes in x doesn't do anything to y. And so if I say my null hypothesis is that beta 1 equals 0, that is equivalent to saying that there is no linear correlation between y and x, right? So when my null hypothesis is beta 1 equals 0, that's if my alternative is that beta 1 is not equal to 0, then what I'm saying is my alternative hypothesis is that there is some type of linear correlation between y and x, right? If I do the same, I could do a hypothesis for checking or whether or not beta naught is 0. That doesn't have the same meaning. It can be useful. We can check it the same way. But really, usually what we care about is beta 1 because it has that stronger meaning. If beta 1 is 0, then there's no linear correlation. If it is not 0, then there is a linear correlation. And so that's what these remaining values are related to. But before I go on to that, is there any questions about that null and that alternative hypothesis? Okay, so with that in mind, if we wanted to do that hypothesis, the nice thing is all the information is here already. Back before, when we set up our hypothesis, then we said, okay, now we got to run our little square root functions and figure out the standard error. Linear regression and correlation questions are so popular that they've just done everything here for you automatically. It is all in here, right? So what are the things we need for our hypothesis test? We usually are curious about the standard error. Boom, that's right there. That's the top number is the standard error for beta naught hat, and then the bottom one is the standard error for beta 1, right? Those are both my standard errors. Next thing I might need is the t-value, because when we test, when we're testing these hypotheses, is using a t-test, not the normal. We're going to use a t-curve, right? And so we end up with a t-value instead of a z-value. And so again, that top one is the t-value for beta naught. The bottom one is the t-value for beta 1 hat. Since this is a t-distribution, I do also need my degrees of freedom, right? Because remember, when we're testing our t-values to get our p-values, for the t-distribution, the shape of the t-distribution changes based on the degrees of freedom. And the degrees of freedom are based on the total number in our set. Now, it used to be we would count them all up and subtract by 1. You don't actually have to do any work here because the number's right there. You can just grab it. It's 989. If you want to know where it's coming from, this data set originally had 991 observations in it. And the reason it goes down to 989 is because we're spitting out two things here, beta naught hat and beta 1 hat, right? So this gets back to when we were looking at that tables like we're doing there, where is the total divided by the the total subtracting off the number of things that we're figuring out here. So since we have two parameters that we are estimating, we actually, or maybe I'm full of garbage. Wait a second. What am I? I could be full of garbage. But we should be subtracting off two. Either way, the point is that we only have the degrees of freedom can be pulled right off from there. Questions on standard error, the t-value, and the degrees of freedom of where we would find them on this chart and where we've used them before. Okay, so the nice thing is all those stats are there, and you might need them if I ask you, hey, what's the standard error, what's the t-value, what's the degrees of freedom? But ultimately, we usually use all those to calculate the p-value, which we don't need to do because it's right there, right? The top one is the p-value for beta naught hat, and the bottom one is the p-value for beta 1 hat. So if the question that I was interested in is there a linear correlation between here, I would set up my null hypothesis is that beta 1 hat equals 0, meaning there is no correlation. And then my alternative would be that beta 1 hat, or I'm sorry, I did exactly the sin I told you guys not to. The null hypothesis would be that beta 1 equals 0, the parameter beta 1 equals 0, meaning that there is no linear correlation. And the alternative would be that beta 1 doesn't equal 0, meaning that there is some linear correlation. And this right here is saying that the p-value for beta 1 hat is a lot of zeros and a 2 after the decimal point. I'm not even going to count. But the point is that if my alpha was 0.05, or even if my alpha was 0.01, or even if it was 0.0001, the point is that my p-value is significantly smaller than that. And so I would reject the null hypothesis that beta 1 equals 0, meaning that I have significant evidence to support the fact to support the hypothesis that there is a linear correlation between the budget and revenue of a movie. And we'll get into a little bit of the specifics on the confidence interval and a hypothesis on the next page of what steps you need. But before we get there, any questions on what's going on this page and how you would grab out the different information that you might need? Okay, so this should not be too excitingly new to you guys. You guys have seen versions of these throughout the entire semester. We've been doing confidence intervals and hypothesis tests forever. In this case, we're just doing them for coefficients, right? For the coefficients of our linear model here, right? And so for the first one, the confidence intervals for the coefficients, this is saying for either beta naught or beta 1, the book calls them B naught and B1, I can build a confidence interval, right? So I'm going to have an estimate, but how good is that estimate? So I've only got 3 parts to this, and there's only one part. You got to do any amount of work, and it's a very small amount of work, right? So you need first your estimate, right? And so your estimate are these right here. So that's going to be where your confidence interval is centered. If you're doing a confidence interval around beta naught hat, then you're going to say beta naught hat is, or for beta naught, for you're doing a confidence interval for beta naught, you're going to center around the estimate and go around there, right? Then the next part is the T star times the SE for whatever one you're testing, right? The SE, super easy, right? That's right here. So whichever one you're doing, just pick the standard error right out of there. You're good to go. The only part that you can't grab directly out of here is T star, right? And so T star, we've done the exact same way here. The only thing you need for a T star is you need first, what is your confidence level, right? If I want a 95% confidence interval, then that means I am going to say, well, then I want 1 minus 0.95 divided by 2, right? Because that's going to take the 95%, 5% divided by 2 and spread it on each end, and I'm going to get 97.5, right? So that's the 97.5, comma, my degrees of freedom, which, hey, are right there, right? So I could put that there for this one. And then I said T star here, but to find T star, the function we're using is QT, right? Whoops, don't know what I did there. I have jacked everything up. There we go. So it'd be QT, like we did before, and then using your confidence level to figure out what percentile you need there, comma the degrees of freedom. All the information is there. If you need help on that, go back to one of the labs or the homework where we calculated T star, because it's the exact same way. It's just you need the estimate, which is on that chart. You need the standard error, which is on that chart. And then you have to calculate T star, which the only thing you need on there is the degrees of freedom, which is on that chart. So that is how we build a confidence interval around our coefficients beta naught or beta 1 or B naught or B1 in the book's terms. Any questions on confidence intervals? Okay, hypothesis testing for coefficients are similarly simple, but you got to go through the steps, right? So prepare, identify your parameter of interest. It's either going to be beta naught or beta 1. List your hypotheses. It's going to be that either beta naught or beta 1 equals 0, and then your alternative is either going to be beta naught or beta 1 doesn't equal 0, right? Establish your significant level. That's your alpha. Done with the prepare check. Okay. Now the check step, that's probably going to be the one where you have to do the most work, and it's not that much work, right? So this is where you need to check those 4 conditions for our linear regression, right? The linearity of the model, the normality of the residuals, the constant variability of the residuals, and the independence of the observations, right? Those are easily checked by the 4 diagnostic plots that we did last time, and that they are explained by that. I think it's in lesson 29. There was a link to University of Virginia. I highly recommended you guys bookmark. And so be able to do that, run those plots, and then be able to explain them. But remember, in anything like a lab that I ask you guys to do, you need to acknowledge that you need to do the check. You need to spit out the 4 plots correctly, and then you need to check each one of these with an explanation. So at a minimum for a check step, what I should see is, hey, we're going to check. Here are the 4 plots put out so I can actually see them. And then I need you to check each one. Linearity. Tell me which graph is the one that does linearity, and tell me why it either does or doesn't. If you just show the graphs and say, hey, we're good, that's not enough. If you say, here's the graphs, and you say linearity pass, normality pass, variability pass, independent observation pass, that's also not enough. I need you to show the graphs. I need you to check each one by telling me which graph you were using to check it, and then a short explanation of saying linearity. Line looks straight, about same number above and below, so it is. Normality. The QQ plot looks straight, so we're good. Constant variability. The dots are closer to one end than they are the other. So it seems like constant variability may not be met. Independent observations. All the dots are within Cook's distance, so we're good on that, right? So print the charts, acknowledge which chart is for which check, and then a short explanation of why it does or does not pass each check. I need at least that for each one, or else I got to ding you. Okay, calculate. All the calculate is build that model and spit out that summary. All the numbers we need are in there. That you don't have to do any actual calculation. That just means make R do the calculations. Because then the last part is the conclusion, which is you showing that you know how to pull out and interpret the things from that calculation, right? So the conclusion at a minimum should say your p-value for your null hypothesis that you pulled out from that summary, compare it to the alpha, tell me if it's greater or lower than alpha, and if that means you reject or don't reject. And then I need you to tell me in words, at least very shortly, what that means. So a sample answer for ours might be our p-value is 0.00002, which is less than our alpha of 0.95. Therefore, we reject our null hypothesis, which means that there is strong evidence, there's statistical evidence or strong evidence to suggest that there is a linear relationship between the budget of a movie and the revenue of a movie. The only other thing that you might have to add is any caveats that you might have had. So if there was anything that was strange or didn't pass, you would say all that and then say, comma, however, we should be skeptical of this result based on the failure of our normality check, or the fact that we had one observation that did not seem independent, right? So that's what I need. The p-value, the comparison of the alpha, whether or not you reject or not, what that means in terms of the problem, and then any caveats that you have. That's what has to be. Okay. Any questions on the setup here for confidence intervals for coefficients and hypothesis tests for coefficients of linear models, linear regression models, least square linear regression models? Okay, you guys are very quiet, which means either I am an amazing teacher, or it means that someone stuck the COVID swabs too deep up your nose this morning and hit the part of your brain that is kind of turning you off today, which both are valid responses. Well, maybe me being the amazing teacher, not incredibly valid. There's some track record that shows that I do make mistakes from now and then. All right, let's shift gears and spend the rest of the class working in examples. So let me see. Oh, shoot, I don't have it on me. I'm going to give you guys read this example while I find something for you. I'm going to go here and here. And I'm going to go here. I know this is the favorite part of classes when you guys get to watch me navigate through file structures, especially when the internet is slow. It's like adding commentary back to my lessons. All right, so let's do that. So close to the piece of information that I want. That was, oh my gosh, just load. There we go. That was far harder than it needed to be. All right, goodness gracious. All right, so I'm putting in the chat there. That's a link to my instructor folder of the data for this. But basically, the short version is that my brother is having issues again, but this time it has to do with correlation, right? So what I just sent you was a data set that I put together that has data from the Seattle Seahawks, which is a football team for the last 20 years on their starting quarterbacks. There's a lot of variables in there. Some of you guys who follow football more probably will recognize what the abbreviations mean, but the more important things for this question is that the variable ATT is for attempted passes. It's basically how many times do you try to throw the ball. TD is the number of touchdowns, and INT is the number of interceptions. And so basically what this is asking you to check here on the first one is that my brother is claiming that there is no linear correlation between attempted throws and touchdowns made. Whereas my sister is claiming that there is no linear correlation between attempted throws and interception. So that represents two separate hypothesis tests. So whether you are interested in trying to prove my brother wrong or my sister wrong, I am equally happy on either. And so what I would ask is to see if you can set up the hypothesis test for one of those and work it all the way through. I'm not asking for this to be turned in. You can show me examples of it. This is not about getting a full, lab quality work done. When you get to the actual lab, you'll be doing that. But this is more, I want you guys to feel comfortable about knowing how to tell R to do something and being able to interpret the results. So I want you guys to download that CSV, try to load it up, and then play with it a little bit. See if you can make scatter plots of the variables that we're talking about. Give me a gut intuition. Does it look like yes, no? Then then do the formal hypothesis test and tell me, does the hypothesis test at what alpha can you tell me that what is your null hypothesis? Do you reject it or not? And then also, I'm going to want to see your normality conditions. Were the normality conditions met for each one of these tests? And so that's what I'd like to see you guys working on. And if you get stuck at any point, like same rules apply as last time, ask me sooner rather than later. If you would rather, instead of looking at a hypothesis test, look at a confidence interval, then you can look at that side bet there down at the bottom. And that one requires you guys to think a little bit to be able to interpret the question, right? So my other sister, Caitlin, is saying she claims that the Seahawks make about one touchdown for every 10 attempted passes. And she says she will pay if a 95 confidence interval proves her wrong. So there's two questions in there, right? One is, what is she claiming when she says that the Seahawks make one touchdown for every 10 attempted passes? And then once you figure out what she's claiming, then you need to construct a 95% confidence interval to see whether or not that proves her wrong or not. So I will, same as before, at the end of today, I will send out my version of the answer so you guys can compare it. But I'd like you guys to use the next 15 minutes as much as possible to dig in and see where you get stuck. Does this make sense? Is it just an issue of taking time, or is there something in here fundamentally confusing you about how to bring it up, how to call the functions, and how to interpret the data? So I'm going to mute my mic, but bug me either by chat or by just speaking up here if you have any questions on this as you work through it.
Sir, I have a question. Can we like should we go through the like each sibling's claim separately, or should we like
Yeah,
go through them kind of like
so you'd have to go through them separately, right? So you can pick one
right?
because they're two
Oh, okay,
separate
awesome.
claims, right? One is saying that there's no linear correlation between attempted throws and touchdowns, and the other one is that there's no linear correlation between attempted throws and interceptions. So in each one, the X variable is the same, but in each one, the Y variable or the response variable is different, right? And so yes, it would definitely be two separate hypothesis tests to claim them. If you were very clever, there is some multiple regression techniques that you could maybe do to do it all at once. But for our methods right now, is two separate questions that need to be tested separately.
Okay, thank you, sir.
Yeah, definitely. I had people ask, so I put up there. There's the quick link to the site with the explanations of the diagnostics for the checking the conditions, and then right after that is a sample code for calculating T star. Like I said, you can go back to your lab or anything. It's the same way we've done it before, right? But it's basically to find a T star, it's QT, and then you have to give it the one minus the depending. So this would be 5% confidence interval, 0.05 divided by 2. And then the degrees of freedom, you just give it whatever your degrees of freedom are. In this case, I'm setting it to a variable equal to DF1. You would just have to pull that out of your summary statistics to give it to it if you wanted to calculate the T star for a confidence interval. Okay, we are coming down to the last 4 minutes here. Um, as we are wrapping this up, like I said, continue. Feel free to continue working this. I will send out my versions of explanations of this later today if you just kind of look at it and see if you have any additional questions. But in general, I haven't seen too many responses on here. I'm just curious if that is you guys taking the time and kind of working through, and it just is takes a little bit to get started, or if there's anything in particular that you guys are getting stuck on, or that you got stuck on and that you're good to go now. I'm curious, just so I can kind of figure out as moving forward, what are the parts we want that I should focus on, or anything that you have. And if you don't know now, you send me something after class or as you're looking at it, because as I look at the rest of here, we don't have a whole lot of new things, right? Next, we're going to introduce multiple regression. We're going to look at different versions, but it's basically going to be just looking at different versions of the same thing. So I really want to take the time to make sure you guys feel comfortable navigating a problem like this. And if there's anything that you're not, I'd like to know if it's how the question is asked, how to draw on the data set, how to build the model, how to extract the stuff you want, or how to explain it. Those are all things I want to make sure you guys don't have any issues with. So, either let me know now or send me messages and we can talk about it offline or during the next class.
So do you have a finished solution for this problem?
I do. I have I stole some of the code from Captain Forbes. He did it in comparing GRs. I am a bad person, so I just look for ways to have it relate to football and my brother looking bad if I can. But yes, I have a full worked out version. I was going to send it out at the end of today. The only thing I was going to add is I was going to try to add some comments of what the code is doing, and maybe try to give short, succinct versions for the check phase of, hey, here is the what I'm looking for on here, to kind of give you not just a code idea, but since so much of this is now are doing the heavy lifting, also the what would be your part of it version as well. Which I can share now if you'd like. But like I said, I wanted everyone to work on it. I was going to kind of wait until after I was done teaching my classes and then throw it out like I did with the last example, and then take a look at that. And then if you have additional questions, if it just made more questions or didn't answer the particular question you have, then let me know, and we can spend some or all of next class working on that. All right, I only got about 50 seconds left here, which I am happy to give back to you guys if you like, because I am that benevolent of a person. And if you guys have questions later, send it to me there. But otherwise, take a look at that, work on that. Make sure you are feeling prepped for the homework and the quiz. If you got any questions on the quiz, or you got some code or things that you're looking at and you want me to look at, I'm available between now and then. But otherwise, work on that. I know life generally sucks on a lot of aspects these days, but try to focus on the parts that don't suck, which I know is easy to say as someone who gets to leave base, but it makes you feel better. I leave base to go home and then deal with 3 children who are in various states of lockdown from 3 different schools, and a dog that is recovering 8 weeks on surgery that requires constant care. And then I spend my extra time doing lesson prep and grading your stuff. So I'm not saying trying to have a wine competition, but just saying everyone's working on it. And without getting into a political thing, I will say all the decisions they're making right now are because they ask us as well, and we so want you guys to graduate on time and get your jobs on time, because I do not want to follow. I have multiple friends at other universities that are just pushing deadlines out a semester or a year, which just means people aren't getting their jobs, they're not getting their education. And so we're trying to do it not because we're jagoffs. I mean, I can't speak for everyone. There's probably at least one jackoff around here, but we're doing it because we want you guys to get a diploma, get a job, get medical care and get to go start being an officer and get out of here. And the more mistakes we make, the longer that takes. So help out with that. And like I said, I'm always here if you want to send me an EI, if it's only not to do math, but just to bitch about everything. And because you can't talk to anyone but your roommate, and I suddenly have become an okay second choice, I'm always free for that. Other than that, I will see you guys on Wednesday, and I hope the week goes as good as it can.
Thank you.
Thank you, sir.
Yeah, definitely.
Thank you, sir. Have a good one.
I'm going to do my absolute best.